At the moment the first Buk M2 missile left its rail over Bryansk Oblast, the cost-exchange ratio of this engagement was already settled. The missile costs approximately $1 million. The target it destroyed, an FP-1 drone carrying a Luneburg lens instead of a warhead, costs $55,000 and contains enough foam and fiberglass to fill a recycling bin. Russia fired 8 of these interceptors in the opening 10 minutes of the Ust-Luga strike package. $8 million destroyed $440,000 worth of decoys. The Buk battery that fired those 8 interceptors has 4 missiles remaining. 30-plus contacts are still on the scope. The doctrine that says, engage the largest radar return first, has burned through 2/3 of the battery's magazine against targets that were designed to be engaged and destroyed. The Luneburg lens, a sphere of layered plastic and glass costing less than a car tire, just turned Russia's most expensive air defense doctrine against itself. What follows is the complete systems analysis of the Ust-Luga engagement. Every layer of Russia's air defense architecture that engaged the Lutey drone package, what each layer cost per intercept attempt, why each layer failed to achieve its designed function, and what the Bukom 3 Valley repositioning reveals about the adaptations Russia is being forced to make as the cost-exchange ratio continues to run against it. The analysis proceeds layer by layer from the outer Nebo SVU detection network through Bukom 2 magazine depletion, Su-35S low-altitude intercept constraints, Pol 21 jamming, and GNSS spoofing, Bukom 3 Valley positioning, Pantsir-SMD terminal defense, and finally, DSHK and cord heavy machine gun perimeter fire. Each system examined for what it achieved, what it cost, and what it failed to prevent. But the architecture begins with the decoy, and with the specific physics that makes a $55,000 drone disappear behind a $1 million problem. The Luneburg lens is a passive radar enhancement device, a sphere of concentrically layered materials with a graduated refractive index that returns radar energy directly back to its source regardless of angle of incidence. The effect is a radar cross-section amplification disproportionate to the lens's physical size. An FP-1 drone's natural radar cross-section is approximately 0.01 square meters, in detection terms, equivalent to a pigeon. A Luneburg lens attached to the nose of the same airframe returns a cross-section between 1 and 5 square meters, equivalent to a cruise missile in the frequency range used by Russia's Buk engagement radars. The engagement control station cannot differentiate between a Luneburg-equipped FP-1 and an actual cruise missile using radar return data alone. The doctrine response, engage the largest return first, is correct given available information. It is also exactly the outcome Ukraine designed for. 8 Buk M2 interceptors at approximately $1 million each. Total cost $8 million. Destroyed 8 FP-1 decoys at $55,000 each. Total cost $440,000. The cost-exchange ratio is 18.2 to 1 in Ukraine's favor on the decoy engagement sequence alone. The Buk battery then has 4 missiles remaining against a scope still showing 30-plus contacts. The engagement control station faces a binary choice: cease fire and preserve remaining missiles for the real threat, or continue engaging and risk empty rails when the warhead-carrying Lutiys arrive. It continues engaging. This is the designed outcome of the decoy doctrine, not primarily to preserve the real drones from interception, but to force the engagement control station into a magazine management crisis before the real threat arrives. Quick note: you're watching Defense Wire. If you haven't subscribed yet, now's the time. The 12 AN-196 Lutiys that slip through the depleted engagement zone cross into Russian airspace at 200 feet, below the radar horizon of the depleted Buk batteries, and below the effective detection threshold of the S-400 system at Ust-Luga, which is optimized for cruise missile detection at altitude. Two Su-35S fighters scramble to intercept. The engagement analysis here is straightforward. The Su-35's Irbis-E radar operates in X-band, short wavelength, high resolution, excellent against aircraft-sized targets. Against a 0.01 square meter drone at 200 feet over terrain, the return drowns in ground clutter. The pilot switches to IRST, infrared search, and track. The Lutiys gasoline engine produces exhaust at 400 to 500 degrees Celsius, against a background thermal environment that includes farmhouses, vehicle engines, and heated structures across a 10-kilometer sensor footprint at 600 miles per hour. Isolating a single exhaust signature is not a targeting problem. It is a signal-to-noise problem that IRST at that speed and altitude cannot reliably solve. To achieve a firing solution with the GSH 31 30mm cannon, the Su-35 pilot must slow to approximately 300 km per hour to avoid overshooting a target moving at 150 km per hour. At 300 km per hour, at night, at low altitude, close to the Su-35's minimum safe speed in the altitude temperature environment, the aircraft is at the edge of its flight envelope. Russia lost an Su-30SM over Crimea in October 2025, conducting this same type of low-altitude drone intercept. The pilot fired 2 cannon bursts without achieving a confirmed kill. He disengaged. Total fuel cost of the intercept attempt: approximately 15 minutes of full-power flight at low altitude. Total effect on the Luty package: none. Cost per intercept attempt: the operational cost of an $85 million airframe at the edge of its envelope, with fratricide risk, against a target that costs $200,000 and cannot deviate from its programmed path. The Pol-21 GPS jamming and GNSS spoofing sequence introduces the navigation degradation that defines the engagement's final outcome. Pol-21 broadcasts jamming noise across GPS and GLONASS frequencies simultaneously. The Luty switches to dead reckoning, gyroscopic inertial navigation combined with terrain camera optical flow cross-reference. Over 90 minutes of GPS denied flight through the Smolensk-Pskov corridor, gyroscopic drift accumulates approximately 800 meters of positional error. When GPS signal is restored, the drones accept the fix, but the restored signal is a GNSS spoofing injection, a counterfeit constellation transmission indistinguishable from authentic satellite signal. 3 Lutiys accept the spoof and drift into NATO airspace, impacting Estonia, Finland, Latvia, and Lithuania. The Lutiys, equipped with terrain camera cross-reference capability, detect the coordinate mismatch against the stored terrain library and override the counterfeit fix. The terrain camera is a commercial off-the-shelf component. The spoofing system it defeats is a purpose-built electronic warfare installation. The 800-meter gyroscopic drift from the earlier genuine jamming, however, remains baked into the navigation solution regardless of the spoofing outcome. The Buk-M3 Valley repositioning is the most operationally significant adaptation in this engagement. Standard air defense doctrine places medium-range SAM batteries on elevated terrain to maximize radar horizon and engagement range. The Ust-Luga duty officer, having observed 5 identical Luty approach profiles over 16 days, southeast axis, Luga River corridor, treetop altitude, repositioned a Buk-M3 battery onto the valley floor, pointing its radar down the exact approach corridor. The 9M317MA missile has a minimum engagement altitude of 15 meters and range up to 70 kilometers. But inside the valley, the effective engagement range shrinks to under 10 kilometers. The trade-off is reaction time. The radar already knows the exact azimuth and altitude of inbound drones. 2 Lutiys are destroyed in 4 seconds. The third Luty, offset 800 meters from the expected track due to the accumulated GPS jamming drift, created by Russia's own Pol-21 system 4 hours prior, is outside the pointing box when detected. The missile fires in tail-chase geometry, achieves proximity detonation 40 meters behind the drone, damages the fuselage and fuel system, but does not destroy the engine or warhead. The Luty continues on the mission. The Pantsir-SMD terminal layer represents Russia's most capable near-term response to the drone swarm cost problem. The standard Pantsir carries 12 interceptor missiles. Against a swarm of 20 drones, magazine exhaustion is mathematically certain. The SMD variant carries 48 smaller purpose-built interceptors with a networked sensor feed from all radar and EO systems around the port. It achieves 1 confirmed kill in the terminal engagement. DSHK and cord heavy machine gun positions, 12.7mm systems, World War II-era technology, truck mounted with thermal optics. Account: jammer accidentally saved the drone it created the vulnerability for. Machine guns and thermal scopes on the port perimeter account for 1 more Luty. The upgraded Pantsir-SMD, carrying 48 smaller purpose-built interceptor missiles instead of the standard 12, designed specifically to kill cheap drones without burning million-dollar interceptors, gets another. 3 reach their terminal dive. The infrared seeker locks the thermal bloom of 50,000 cubic meters of crude oil storage tanks against frozen March ground. At 4:02, the first 50-kilogram warhead punches through the steel shell of a Transneft Baltica storage tank. Crude ignites. Black smoke climbs over Luga Bay. 8 seconds later, the second drone hits 200 meters south. Then the shrapnel-scarred drone arrives, leaking fuel from 3 holes, flying sideways on a shredded control surface. Navigation computer, completely oblivious to the fact that it is barely airborne, and slams into a loading berth at the waterline. The petroleum pipeline ruptures. Fire runs down the berth and into the water. 6 hours and 20 minutes, 950 kilometers. Jamming, spoofing, a supersonic fighter, and a valley ambush. And the most damaged drone in the package hit its target last. If you want to understand the cost math behind every layer of this engagement, what each intercept cost Russia versus what it destroyed, check our analysis of the Luneburg lens doctrine and the full cost exchange breakdown. And if you want to see what this operation means for Russia's Baltic oil export revenue, our strategic impact breakdown will give you the full picture. Subscribe to Battle Pulse so you never miss what comes next.